Okay, let's jump right into something pretty wild today. Imagine you need to measure something almost impossibly small, like the thickness of just a single layer of molecules.
Yeah, really tiny stuff.
Exactly. But you're trying to do it in a really terrible environment. Maybe there's, barely any light getting through your sample.
Or the opposite problem, maybe there's just a ton of distracting background light bouncing all over the place.
Right, like trying to spot a single grain of sand in a bright sunbeam. It feels impossible. How do you get precise, accurate measurements in those kinds of messy, noisy conditions?
Well, that's a fundamental challenge, isn't it, in so many scientific fields. Your traditional high-precision tools, they really struggle when you have samples that absorb or scatter light heavily.
Or when you've got all that background noise?
Absolutely. Getting down to the nanometer scale, billions of a meter, demands incredible sensitivity. And those kinds of hostile environments just, well, they kill that sensitivity.
And that's really what makes this new research from the University of Illinois so compelling, I think. They've developed a new tool that seems to tackle these difficult conditions head-on, achieving revolutionary precision measurement at that nanometer scale by doing something pretty unexpected.
Yeah, they're actually leveraging the bizarre fundamental properties of light at the quantum level. This isn't just a small tweak or an incremental improvement. No,
way.
it looks like a genuinely new type of tool, a quantum-enhanced interferometer, they call it, and it promises to be faster and far more robust than what we had before.
Better than classical methods and even better than earlier stabs at using quantum for this.
That seems to be the case, yes.
Okay, so for this deep dive, our mission is to really unwrap what's going on here. How does this technology actually tap into quantum physics? What makes it so much better in those, challenging real-world scenarios?
And maybe most importantly, what could this actually mean? For you, for me, for everybody, where could we actually see this tech making a real difference? Maybe medicine, material science? Who knows?
It sounds like a fantastic example of how, pushing the boundaries in fundamental physics can sometimes yield these incredibly practical, almost immediate technological advantages.
Exactly. It's not always just theory.
Okay, so to really grasp the leap forward here, maybe we should ground ourselves in the basics first. We probably need to talk about classical interferometry. That's kind of the foundation for precision measurement in so many areas, right?
Absolutely, yeah. Good starting point. At its core, interferometry is all about using the wave nature of light. It's like waves on water can interfere.
Crests meeting crests, troughs meeting troughs.
Right. Light waves do the same thing. When wave crests align, they reinforce each other. That's constructive interference. But when a crest meets a trough, they cancel out. That's destructive interference.
Okay, so you start with a beam of light, usually a laser, and you split it into two paths.
Exactly. Think of them as two arms of your measurement system. One arm might just be a simple reference path, bouncing off a mirror.
And the other arm is where you put the thing you want to measure, the sample.
Right. The light travels down both these arms, reflects back, and then the two beams are recombined. Now, if those two paths were exactly the same length,
the waves might just cancel out perfectly.
Yeah.
Destructive interference.
They could, yeah. But if you put a sample in one arm, say a really thin film, even if it's just nanometers thick, it slightly changes the effective optical path length for the light going through it.
So it takes a fraction longer or shorter, effectively.
Precisely. And that tiny change in path length means when the light waves recombine, they no longer cancel out perfectly. Instead, you get some amount of interference, and that creates a detectable signal.
And by precisely measuring how that interference pattern changes, you can figure out the thickness or maybe other properties of that sample, down to incredible precision.
That's the principle. And it's been astoundingly successful. I mean, classical interferometry is why we can detect gravitational waves.
Which are those mind-bogglingly small ripples in space-time, right? Stretching distances by less than the width of an atomic nucleus.
Over kilometers. It's amazing sensitivity.
And it's used right inside hospitals, too. That OCT thing, optical coherence tomography.
That uses interferometry to measure the layers in your retina, helps doctors diagnose eye diseases very precisely without ever touching your eye.
Okay, so it's powerful stuff. But as you said, classical interferometry hits walls when you're dealing with those really challenging samples or environments we mentioned at the start.
Right, like trying to measure the thickness of a really thin film that maybe doesn't let much light through if your sample absorbs or scatters a lot of light.
The signal coming back from that arm gets super weak.
Exactly, and when that weak signal recombines with the light from the reference arm, the overall interference signal becomes very faint, very washed out.
Like trying to see a tiny ripple in a pond when you can barely see the water's surface.
Yeah, good analogy. And the source material also highlights that other big problem: background light. Any stray light getting into your system just adds noise.
And that noise just obliterates the delicate interference signal you're trying to measure. They had a great analogy for that too, like trying to see subtle details in an overexposed photo.
Right. Everything gets saturated, bleached out. You lose all the detail, kill your sensitivity.
So how do you get past these fundamental limits that plague the classical systems?
Well, this is where they took that deep dive into quantum mechanics. Instead of treating light just as continuous waves, they started thinking about it as discrete packets of energy.
Photons.
Photons, exactly. Individual particles of light.
Okay, so you're not sending a continuous beam anymore, but like single photons, one by one.
Pretty much. In their setup, they send a single photon down each arm of the interferometer. But crucially, these aren't just any old photons.
There's a trick.
There's a quantum trick. They're quantum mechanically linked and tangled, which we need to get into.
Okay, but hold on. How does sending just one photon at a time through a sample that absorbs light actually help? Wouldn't that single photon just get lost most of the time?
That's the intuitive question, but here's the key quantum insight. It directly addresses that low transmission problem. While yes, many individual photons might get lost passing through a difficult sample, the measurement isn't based on detecting just one photon that made it. It's based on detecting both photons of an original pair together at the output and observing their quantum interference.
Both photons together. Okay.
Yeah, the lead author, Colin Lualdi, explains it well in the source. He says basically, as long as you detect the pair of photons that traveled the two paths, the contrast of the interference signal, the clarity remains high.
Even if lots of pairs get lost along the way.
Exactly. If a pair gets lost because, say, one photon didn't make it through the tricky sample, you simply don't count that event. You ignore it. But the pairs that do make it through,
they still contribute to a clear, high-contrast signal.
Precisely. Even if there are only a few of them getting through. That's a massive quantum advantage over classical light, where the strength of the signal determines the contrast. Here, it's about detecting the pair.
Wow, okay. It's like you're filtering out all the failed attempts, the lost photons, and only counting the successful pairings. And those successful pairs inherently preserve the signal's quality. That's clever.
It really is.
So what about the other big problem? The background light. That stuff's usually everywhere.
They tackle that using time. Ultra-precise timing. See, the photons they generate are created in pairs at a very specific moment.
Okay.
So by measuring the interference signal only within a very, very narrow time window, right around when those photon pairs are expected to arrive.
How narrow are we talking?
Fractions of a nanosecond. The paper mentions about 100 picoseconds. It's incredibly short.
Wow.
And because it's so short, they can effectively filter out nearly all the background noise. Background light photons tend to arrive randomly, right?
Yeah, they're not synchronized.
So the chance of a stray, random background photon hitting their detector within that tiny, specific 100 picosecond window, exactly when their paired photons are expected, it's extremely low.
Got it. So photons plus these tiny time windows solve the low transmission problem and the background noise problem. Sounds great.
It is great.
But achieving that ultimate goal, that nanometer precision, with the sort of traditional two-photon quantum methods, still had its own set of headaches, didn't it? I think the source mentioned that.
You're right, it did. While two-photon interference definitely offered advantages over classical, getting down to nanometer scale precision usually required one of two things, both problematic.
Oh, where were they?
Either you had to integrate your data for a very long time, like hours sometimes, which obviously isn't practical if you want quick measurement.
Right, not ideal.
Or you had to use photons with a very broad range of colors, what physicists call a broad bandwidth.
And working with those broad bandwidth quantum photons?
Mm-hmm.
Is that hard?
Apparently, yes. Quite technically challenging to generate, manipulate, and detect properly in a lab setting.
Okay, so that brings us to the core innovation from the Quiet Group at Illinois. They found a way around that technical headache.
They did, by using something they call extreme color entanglement.
Entanglement. Okay, that's the spooky action at a distance thing Einstein wasn't sure about, where two particles are linked no matter how far apart.
That's the very one. They create pairs of photons where the two photons are entangled, linked, but not just in any old way.
How so?
They specifically entangle a property related to their wavelength, or you could say their color. And it turns out entangling their color is the key to boosting the interferometer's sensitivity to those tiny path changes we talked about.
Huh. So the entanglement itself makes the measurement more sensitive.
Well, entanglement in general offers sensitivity advantages in metrology, yes. But the extreme color part is where they really made their breakthrough for achieving nanometer precision relatively easily.
Extreme color. What does that mean exactly?
Yeah, it means that instead of needing that difficult broad spectrum of colors, that wide bandwidth,
Yeah.
they found that by entangling photons that have very different colors, even if each color itself has a narrow bandwidth, they could achieve even higher sensitivity.
Wait, hang on. So using a narrow bandwidth photon at one color entangled with another narrow bandwidth photon at a very different color.
Yeah.
That's actually better for sensitivity than trying to wrestle with a difficult broad spectrum.
Exactly. It sounds counterintuitive, doesn't it? But apparently, the greater the difference between the colors, the wavelengths of the entangled photons, the more sensitive the interferometer becomes to tiny path length differences.
Wow.
It's a consequence of how the quantum entanglement works. Lualdi uses a nice analogy. Instead of needing the whole span of colors, like in the broad bandwidth approach, he says, with entanglement, we only need to work with a little bit of blue and a little bit of red. Or, in their actual experiment, they used photons with wavelengths of 810 nanometers and 1550 nanometers.
Which are invisible to us, right? Infrared.
Correct. Both are in the infrared. But the key is the difference between 810 and 1550 is large. That gives them that extreme color separation and thus high sensitivity.
That's brilliant. Finding a different route to get the necessary sensitivity without all the technical pain of broad bandwidth light. That's really smart.
It is, and this specific design also gives them speed. The source mentions their setup generates hundreds of thousands of these entangled photon hairs every second.
Hundreds of thousands a second. That's fast.
It's a very high rate for this kind of quantum source, and that high rate is crucial. It means they can collect enough data to get a clear signal much, much faster than those previous quantum methods that needed hours.
So you get your precise measurement in seconds.
That's what they demonstrated, yes. Seconds.
And they really put this system through its paces, didn't they? With a deliberately difficult sample.
They did. The source describes testing it on a metallic thin film that was specifically engineered to have very low optical transmission. Exactly the kind of sample that gives classical systems fits.
The nightmare scenario for traditional methods.
Precisely. And importantly, they didn't just measure it with their new quantum tool. They took the sample to collaborators for independent validation using a different technique.
What technique?
Atomic force microscopy, or AFM. That's kind of a gold standard for measuring surfaces at the nanometer scale, but it works very differently. It uses a tiny physical probe to feel the surface.
Okay, so a totally independent check and the results. Did they match?
Perfectly, according to the source. The thickness measurements from their quantum interferometer matched the independent AFM results spot on.
And they did it in seconds on this really difficult sample.
Exactly. Accurately measured the thickness of this challenging metallic film in seconds. That validation is incredibly powerful. It shows this isn't just a cool theoretical concept in a lab notebook.
No, it's a functional tool delivering real-world results, even under demanding conditions.
Yeah. And what really jumps out from the source material, I think, is the emphasis that this is actually a fairly rare case of a clear quantum advantage.
Meaning, using quantum mechanics to do something fundamentally better, faster, or more robustly than any classical method could.
Exactly. And not just better in theory, but with immediate practical applications. It's not confined to some high-level physics lab doing only fundamental experiments. This thing looks ready to potentially go out and do useful work.
And the potential applications they mentioned? They seem incredibly exciting and really diverse.
They really are. Think about medicine, for instance.
Okay.
Because the tool uses such incredibly low light levels, literally just 2 photons at a time, pinging the sample, you could potentially image really delicate, light-sensitive biological tissues.
Like layers within the brain during surgery. Or inside the retina again.
Potentially, yes. And maybe much faster over larger areas than current invasive techniques or even things like AFM allow.
You could even study things like algae or other photosensitive organisms in their natural state, right? In the dark, maybe? Without blasting them with bright light that changes how they behave.
Absolutely. It could open up entirely new ways to do non-invasive biological research, studying things in their native environment.
And that background light rejection feature. That sounds like a game changer for applications outside the controlled lab environment, too.
For sure. Imagine remote sensing or maybe monitoring systems. You could potentially measure properties of distant targets, maybe something that only reflects light very faintly.
Even in broad daylight.
That's the idea, yeah.
Yeah.
Because the system is so good at ignoring all that ambient background light.
And for advanced materials science.
Well, it seems perfectly suited for situations where other tools fail, characterizing samples with very low transmission, or highly sensitive biological samples, or materials that you absolutely cannot touch with a physical probe like AFM uses.
That less invasive nature, just using light, must be a massive advantage for delicate samples.
Huge advantage. And because it's fast, you can start to think about measuring change as it happens.
Like dynamic processes.
Exactly. The source mentions its potential for studying things like nanometer scale vibrations in structures or materials. Measuring those kinds of tiny, rapid movements is apparently very difficult to do accurately with most current methods.
That's pretty mind-blowing, isn't it? How they've taken something from the absolute frontiers of fundamental physics, entanglement, quantum interference.
Stuff that sounds like science fiction.
Right. And built a practical tool that pushes the limits of measurement itself. Professor Quiet is quoted saying it potentially hits the quantum limit of how much information can be extracted from a system using light.
It just really underscores how sometimes the most practical, useful breakthroughs come directly from trying to understand the most fundamental aspects of reality. It's not always an obvious path.
So looking ahead, what's next for this? Are they planning to build devices?
The researchers are definitely thinking about how to tailor this technology for other specific uses, maybe integrating it into existing microscope systems or really honing that capability for measuring vibrations at the nanoscale.
Refining it for specific jobs.
Yeah, exactly. The foundation is clearly built, and now it's about refining and applying this powerful new capability where it can make the biggest impact.
Okay, so to wrap up this deep dive then, we've explored a pretty revolutionary new quantum tool developed at the University of Illinois. It provides ultra-precise nanometer-scale measurements. And crucially, it's faster and far more robust in challenging conditions like low light transmission or high background noise than classical methods.
And it achieves this incredible performance by really cleverly harnessing the power of quantum mechanics, specifically using what they call extreme color entanglement of photons to boost the sensitivity.
And using that very precise time window to just ignore all the background noise.
Exactly. It's a really powerful combination.
It feels like a strong example of fundamental quantum physics transitioning pretty rapidly into a practical, real-world technology with potentially immediate applications.
I agree. And this new ability, this power to precisely measure the incredibly small, even when the conditions are really difficult, it could truly transform fields.
From, say, early disease detection through better, non-invasive imaging.
To understanding the most delicate biological processes without disturbing them, maybe watching them happen in real time.
To characterizing new materials with unprecedented detail, it really gives us a sharper, clearer window into that whole nanoscale universe.
A universe that's foundational to so much of biology and technology.
Absolutely. Well, this has been a fascinating deep dive into the cutting edge of quantum measurement. If you found this as interesting as we did, make sure to like and subscribe so you don't miss future explorations like this.
Definitely. And let us know in the comments what topics you'd like us to tackle next. What areas of science and tech should we deep dive into?
Yeah, great idea. And check out the links in the show notes, too. We'll put more information there on this incredible research from Illinois and maybe some links to related resources, some of which can help support this show. Thanks for tuning in.